and specifically we're going to look at kinetic theory of gases. So our learning intentions are to define ideal gases, list the assumptions of kinetic gases theory, explain why gases deviate from ideal behaviour, and carry out simple calculations using the PV equals nRT equation of state for an ideal gas. So, the kinetic theory of gases attempts to explain properties of gases, and in order to explain properties of gases, we need to make a certain number of assumptions. So, the first assumption is that there are no attractive or repulsive forces that occur between molecules of a gas. So that means gas molecules are independent of each other. So gas particles are in constant, rapid, random motion, colliding with each other and the walls of the container that they're in. Gas molecules are so small and so widely separated that their actual volume is negligible compared to the space that they occupy. And this can be used to explain why equal volumes of gases contain equal number of particles when measured under the conditions of same temperature and same pressure. The average kinetic energy is proportional to the Kelvin temperature. And all collisions are perfectly elastic. That means there is no loss of kinetic energy in collisions, although there may be transfer of energy from one particle to another. So by looking at the assumptions that we've just gone through, we can see that there is certain limitations to the kinetic gas theory, and that is that all real gases do have tiny attractive or repulsive forces between the molecules, and this is discussed in bonding. When we talk about molecules, gas molecules that are polar, they'll have intermolecular forces such as dipole-dipole forces or van der Waals forces. So the kinetic gas theory doesn't hold for real gases, only something called ideal gases. So your definition for an ideal gas is one that perfectly obeys all of the assumptions of kinetic theory of gases under all conditions of temperature and pressure. And the way you remember that, like if something is ideal, it means it's perfect, so it will obey all rules. Now, the big thing is ideal gases actually do not exist. However, real gases come very close to being ideal under two conditions, and that is a low pressure when the molecules are widely spread and high temperatures when the molecules are moving rapidly. So that leads us to our definition of real gases, and real gases differ from ideal gases because forces of attraction and repulsion do exist between molecules, and the volume of molecules is not negligible, and that is another important definition to know. It's also worth noting that the stronger the intermolecular forces, the more the gas moves away from ideal behaviour. So here's a sample question for the ideal gas and kinetic gas theory. It says, state which of the following gases would you expect to come close to ideal behaviour, and which would you expect to deviate most from ideal behaviour? And they give you hydrogen, hydrogen fluoride, ammonia and fluorine. So hydrogen molecules and the fluorine molecules, they are both non-polar molecules with only van der Waals forces between their molecules, where hydrogen fluoride and ammonia molecules are polar with hydrogen bonding and van der Waals forces between their strongest intermolecular forces. The van der Waals forces between the hydrogen molecules are weaker than those between fluorine because there are fewer electrons in hydrogen. So that means hydrogen will come closest to being ideal in behaviour because it has the weakest intermolecular forces. So what we're going to look at now is we're going to look at this ideal gas law, which is PV equals nRT. And with your ideal gas law, you are basically taking Boyle's law, which is PV equals K, Charles' law, which is V divided by T equals K, and the combined gas law of P1 V1 over T1, P2 V2 over T2 equals K. If they're all combined, you form this here in the middle, which is your ideal gas law. You don't need to know how this formula is formed, but you do need to know how to use it. So for PV equals nRT, P is for pressure and it must be in pascals. V is for volume and it must be in meters cubed. N stands for the number of moles that are present. R is a universal gas constant, and that's 8.31 joules per Kelvin per mole, and this will always be given to you in an exam. T is for temperature, and that must always be in Kelvin. And a few little notes here. If you want to convert from kilopascals to pascals, you multiply by 1000. To go from centimeters cubed to meters cubed, you multiply by 10 to the minus 6. And if you want to go from meters cubed to centimeters cubed, you multiply by 10 to the 6. So those can be very useful for this question. So maybe jot them down somewhere to refer to later. So let's do an example. So calculate the number of moles and hence the relative molecular mass of a vapour that is present when 0.63 grams of a liquid occupies a volume of 330 centimetres cubed at a temperature of 100 degrees Celsius and a pressure of 101 kilopascals. So the first thing I want to point out to you in the question is, if you are asked to find the relative molecular mass of a vapour, that indicates that you will be using the PV equals nRT equation. If that's not there, you still do need to check. For example, here we were asked for number of moles, so again we would know it's the PV equals nRT. But if you're asked to find pressure or volume or temperature, you do need to check if it's the PV equals nRT or one of the other equations that we've done already. And the key giveaway there would be number of moles. If it involves number of moles, you'll definitely be looking at the PV equals nRT. So always start by writing out your formula like I have done here. So the next thing, like I always do, I would do P, V, N, R, and T, and fill in for what we know and what we want to know. So if we start with pressure, we know that pressure must be in pascals for the ideal gas equation, but we have it in our question in kilopascals. So we must go from kilopascals to pascals, and to do that you have to multiply by 1000. So for your pressure, you'll do 101 by 1000, and that will give you 101,000. So you get 101,000 for your pressure. We know that our volume, it's given to us in centimetres cubed, but we want to go to metres cubed, so that involves doing it by 10 to the minus 6. So our volume is 330 by 10 to the minus 6. The number of moles is what we're trying to find, so I'm going to label that, keep that as N. R is your universal gas constant, and that's 8.3. And temperature, our temperature is 100 degrees, but we need to add 273 to get that into Kelvin, so we get 373 for our temperature. So at this point you can just fill into your formula, PV equals nRT. So for P we know our pressure is 101,000, our volume is 330 by 10 to the minus 6. N will stay as it is, R is 8.3, and temperature is 373. So what you can do is you can go and rearrange that, and what you get is you will get that N is equal to 0.01076 moles, and that's gotten from rearranging and putting into your calculator. So that is our number of moles found. So we've completed the first part of the question. The next thing we need to do is we need to go and find the relative molecular mass. Now, we know that our 0.01076 moles of our gas represents 0.63 grams when it's in a liquid. So, we just need to go now to find 1 mole of it, because we know that 1 mole of anything is the relative molecular mass. So we need to do the 0.63 grams, and we need to divide it by the 0.01076. And that gives us that 1 mole is equal to 58.55. So the relative molecular mass is 58.55. And that is now the question complete. So that's it for this video. Have a read over the learning intentions to make sure you understand